Hi guys, in the last lecture we saw how to form the Z-bus matrix. So we saw there are four possible modifications in the power system network. One was addition of new bus to reference. There we saw what was the change in Z-bus. It was same as old Z-bus, then a column of rows, column of zeros, and then the new impedance. Then we added new bus to kth bus. What was the change? Z bus kth column transpose of kth column and zkk plus zb. Then we added impedance between kth bus and reference. So it was Z bus minus XX transpose by zkk plus zb, where x was equal to kth column. And the last was impedance between buses so it had the same formula, just Z bus minus XX transpose by ZBB. Now here ZBB was equal to ZJJ ZKK minus 2ZJK plus ZB. X was equal to jth column minus kth column. Okay, so this is what we looked at in the last lecture, and we saw to remove any transmission line between the two buses, we will connect the negative of the same transmission line between the same buses. Okay, so that is the method of removal. In this lecture, what we will be doing is we will study how to use the Z-bus matrix for the case of fault analysis. Now, how did we determine the symmetrical short circuit current? In symmetrical short circuit current, what we were doing is we were converting the network into the Thevenin equivalent, that is one EMF and one impedance. And then we wrote fault current is equal to EMF over, let us say, Z equivalent plus ZF, where ZF is the fault impedance, or we can say Z Thevenin plus ZF. Now when we saw the definition of Z-bus elements, there I told you that the diagonal element at any bus is same as the Thevenin impedance at that bus. So if fault occurs at ith bus, then it implies that Z Thevenin I is equal to II. That means the fault current at ith bus will be EFI over ZII plus ZF, where EFI is pre-fault voltage at I. What is pre-fault voltage? Voltage before the occurrence of a fault. So that is also one of the methods by which we can calculate the symmetrical short circuit current in terms of the Z-bus matrix. Is it fine? So let us take an example of calculating the short circuit current, or calculating the current drawn by some load when it is connected to a bus whose Z-bus is already known. So in this example, it is saying a power system network with 5 buses is given to me. Now we connect a shunt capacitor of impedance minus j.1 to a bus number 4, where voltage at bus 4 is V4 1.05 angle 0. Now Z44 is given to me, j.28. Now how do we draw the Thevenin equivalent of any bus? We will take a voltage source which is same as pre-fault voltage. We will take an impedance equal to Thevenin impedance, that is j.28, and then we will connect the load across the terminals. Then what will be the current? 1.05 J.28 minus J.1. 1.05 upon J.18, that is 5.83 angle minus 90. So this is the current drawn by the capacitor in this problem. You can assume that the capacitor acts as a fault impedance as it is connecting the bus to the reference bus through any impedance. So it is working here as a ZF. Now what will happen is whenever there will be a fault on any bus, then generators connected to the other buses will also supply the fault current. As we saw earlier, whenever there is a fault in fault analysis, we saw all the generators in the system start supplying current. Similarly here, generators connected to other buses will start supplying the current, and we need to know what will be the new voltage at each and every bus. That is, we want to know the change in bus voltage. Now usually fault analysis is done assuming no load condition. That is, let me say that there is a bus J to which there is a generator connected with subtransient reactance Xj, Ej. Now the current here Ij will be 0, due to which Ej will be equal to Vj pre-fault, that is before the occurrence of fault. So induced EMF is actually equal to the old values of the voltage before the occurrence of the fault. Now when the fault occurs, then what will happen? Then the bus voltages will change. How they will change is, we know V bus is equal to Z bus into I bus. So if we apply superposition, delta V bus is equal to Z bus into delta I bus. Now delta V bus will be a matrix where I is the bus at which the fault occurs. This will be my Z bus. Here I have clearly shown the ith row separately. Like this. Now what happens is, earlier there was no current that is being drawn by any bus because we were assuming no load condition. But when the fault occurs, then ith bus supplies a current of if. So what is delta ii? It is if minus 0, which is equal to if. But in ibus matrix, what current do we use? In ibus matrix, the current vector represent the current injected at each and every bus. But in the event of a fault, the bus will be delivering a current. Hence, we have to use a negative sign, because we always take the convention that current is being injected into the bus. Okay, so that is delta ii. Now, other currents delta I1, delta I2, delta IN will be 0. So now we can replace this matrix something like this: 0, 0, minus IF, 0. That means only ith element is non-zero. What about delta V? In case of Vi, initially voltage was Vi pre-fault. Now after the occurrence of fault, the voltage will become 0 due to short circuiting. So delta Vi will be 0 minus Vi, let me write as Vi only, minus Vi, where Vi represents the pre-fault voltage at bus I. So this also I can replace here. This can be written as minus Vi. Now if you concentrate on ith row, minus Vi will be equal to Zi1 into 0, Zi2 into 0, then Zii into minus If, which implies If is equal to Vi by Zii, which is the same expression that we derived earlier, just with Zf equal to 0. Now if you wish to find the change in any other bus voltage, that is delta Vj, then only ith element will be non-zero, that is Zji into minus If. Now minus If will be equal to minus Vi by Zii. Okay, that means the new value of bus voltage will be old value minus Zji by Zii. Now current supplied by the generator at J will be equal to Ej minus Vj by Jxj. Okay, now Ej was equal to Vj old because earlier there was no current in the system. So that means Vj old minus Vj new. So it will be Zji by Zii. So this will be plus Vi upon Jxj. So this will be the current supplied by the generator connected to bus number J. Okay, so that gives the contribution of generator J to the fault current. Suppose 1 kiloampere current goes into the fault, then it will be constituted by many generators. Let us say generator 1, 2, 3. So it gives the contribution of generator J to the fault current. Now let us look at a problem. It is saying for a power system, the admittance and impedance matrix for fault studies are given as follows. We know the pre-fault voltage at all the buses, that is V1, V2, V3. The system was unloaded prior to the fault, that is no load condition. A solid three-phase fault takes place at bus number 2. We need to find post-fault voltage at 1 and 3. Now we need to find V1 new, which will be equal to V1 old minus Z12 Z22 into V2. That means V1 new will be how much? Old voltage was 1 angle 0. Now Z12 is J 0.08. Z22 J.24 into 1 angle 0. That is 1 angle 0, 1 minus 1 by 3. That is 2 by 3, so 0.67 pu. Similarly, V3 new will be 1 angle 0 minus Z32 by Z22 into 1 angle 0. That is 1 angle 0 minus J.16 by J.24 into 1 angle 0. That is 1 minus 2 by 3. That is 0.33 pu. So these are the post-fault voltage at bus 1 and bus number 3. Let us move on to the second part of the same problem. It is asking the per unit fault feed from generator connected to bus 1 and 2. So if we wish to calculate I1, it will be E1 minus V1 by Jx1. Now we need to find this subtransient reactance of generator 1. Now Whenever there is a equivalent circuit of generator, how we replace it? That is EMF in series with reactance. But if we wish to form Y bus, then we saw we have to perform nodal analysis. Then all the voltage sources should be converted to current sources. That means when we convert this voltage source into current source, the subtransient reactance of the generator becomes the reactance between the bus and ground. So somehow, if I calculate Y10, it will be equal to 1 by JX1. How to calculate Y10? By taking the sum of elements in a row. Since we are interested in bus 1 and 2, Y10 will be sum of the elements in this row, that is minus J 5.5. Y20 will be sum of the elements in second row, that is minus J 3. So now it will be E1 will be 1 angle 0, V1 was 0.67. 1 by Jx1 is minus J 5.5. That is 0.33 into 5.5. It will come out to be 1.815 angle minus 90 degree PU. In case of I2, it will be E2 minus V2 by Jx2. Now E2 is 1 angle 0. Now due to fault, the voltage of bus 2 becomes 0 because bus 2 is the bus where the fault occurs. And 1 by Jx2 will become Y20, that is minus J5. So it is minus J5 PU. Okay. So that is the current supplied by the generator connected to bus number 2. In our next problem, it is saying two transpose three-phase lines run parallel to each other, and then we have the voltage drop in both the lines. So remember here, delta VA1, VB1, VC1 represent A phase, B phase and C phase voltage drop in line number 1. Then A phase, B phase and C phase voltage drop in line number 2. Now suppose I write delta VA1. From this matrix it will be J 0.15 IA1, 0.05 IB1 plus 0.05 IC1, 0.04 IA2, 0.04 IB2, 0.04 IC2. Okay. So now if we separate this matrix into two matrices like this, which have only 3 rows, and then this can be separated into further two matrices which have only 3 column. So now if you see this matrix, the first one is identical to fourth and the third one is identical to second. So how can I write these equation? Delta VA1, delta VB1, delta VC1 is equal to J 0.15, 0.05, 0.05, 0.05, 0.15, 0.05, 0.05, 0.05, 0.15, IA1, IB1, IC1 plus J 0.04, 0.04, 0.04, okay, IA2, IB2, IC2. Now we are only interested in zero sequence component or the zero sequence impedance. That means we have to go from A, B, C phase to the 0, 1, 2 domain, that is the symmetrical components. Now when we transfer a transmission line impedances from the phase domain to the symmetrical components domain, the zero sequence impedance becomes Zs plus 2Zm. So here this is the Zs, this is the Zm. So Zs plus 2Zm will become 0.25. In this matrix, this is Zm and this is Zm. Sorry, Zs and Zm. So Zs plus 2Zm will become 0.12. Okay. Now, if you see, the zero sequence voltage in line 1 depends on zero sequence current in line 1 and zero sequence current in line 2. So, the impedance Z011 is, if we neglect the line 2 current, that is IA2, IB2, IC2, what is the zero sequence impedance? That is J.25. So, Z011 is J.25. Now, Z012 is zero sequence impedance if we neglect I01. That is, we neglect this matrix. So, what we are left with is only this matrix. So, the zero sequence impedance Zs plus 2Zm is J.12. Similarly, Z021, since your third matrix was same as second matrix, it will be J.12. And 022, fourth matrix was identical to first, 0.25. Okay. So these are the self and the mutual zero sequence impedances between the two transmission line. Moving on to next problem. Here it is saying the bus impedance matrix of a 4-bus power system is given to me. Now we add a new branch between bus and reference, that is case number 3. Now how we dealt with this case is, we first added a new bus to the existing bus and then made that bus as the reference. So if we add a new bus, then we will be adding a fifth bus. So order of the matrix will become 5 cross 5. So it will be equal to original Z bus. Then we will add a new column which will be the second column. Why second column? Because we are adding the new impedance between bus 2 and reference. So 0.286, 0.3408, 0.2586, then 0.2414. 0.286, the transpose of this, 3408, 2586, then 0.2414, and the last one will be the ZKK, that is Z22 plus ZB, that is 0.2, that is J.5408. Now we saw in the method of Cron's reduction, ZAB new was equal to ZAB old minus ZAP ZPB by PP. In our case, P is equal to 4. So Z22 will be equal to Z22 old, that is J.3408 minus AP, that is 25. 25 is how much? 0.3408. Then 52 is also 0.3408. And 55 is the last element, that is J.5408. How much will this come out to be? 0.3408 minus 0.3408 square divided by 0.5408. So it is J.1260. Similarly, Z23 will be original Z23. Original Z23 is J.2586 minus Z25, that is 0.3408 into Z53. 53 is 0.2586 by J.5408. So the answer will be 0.2586 minus 0.3408 into 0.2586 divided by 0.5408. So it will be J0.0956. Okay. So that will be the Z23. Now let me summarize what we covered in this lecture. We first saw how to find the fault current. It was EF by ZII plus ZF. Then we saw what is the new bus voltage. It was equal to old minus ZJI by ZII VI. Then we saw what is the fault feed from generator connected to bus J. IJ will be equal to ZJI by ZII VI divided by JXI. In the next lecture, we will start with the load flow analysis, and we will see how Y bus is used in load flow analysis and how to determine the voltage at each and every bus.